Hey everybody, welcome back to another lecture video. In this chapter, we're going to take a look at alcohols, phenols, thiols, and ethers. Alright, so you've probably never heard of many of these types of compounds before, at least in their chemical name, but you've probably dealt with them, at least alcohols, phenols, and thiols across your life in a lot of different areas. Anesthesia, for example, typically administered by a nurse, anesthetist. They provide the care during, before, and after medical procedure. And they give you medications such as propofol. And this actually keeps you asleep and pain-free, and they monitor your signs while you're under this anesthesia during a procedure. Propofol is actually a type of alcohol, and we'll look at that. So the learning goal in this chapter is going to be to write the IUPAC names and the common names for some alcohols, phenols, and thiols, as well as to draw their condensed and line angle structures. So we'll start by just figuring out what these different names are. So alcohols are compounds that contain a hydroxyl group, and the hydroxyl group is this OH. You remember from Gen Chem, we dealt with OH minus a lot, the hydroxide ion. Well, this is a hydroxyl, OH, no charge. A phenol is this very special kind of alcohol. It's just a hydroxyl on a benzene ring. So you remember from the last chapter when we were talking about benzene and naming some of the derivatives of benzene. When benzene has an alcohol group, we can call it phenol. When benzene had a methyl group, we called it toluene. Okay. So phenol and methanol are both alcohols because they both contain a hydroxyl. Phenol is just a special kind of alcohol on a benzene ring. Thiols contain SH groups. Now, in the periodic table, sulfur is right underneath oxygen. So these have, they form a lot of the same kinds of compounds. And so when we have a sulfur-containing group here, we call it a thiol. So that's the definition of these three categories. And so again, we're going to write some names, we're going to draw them, and just learn a little bit more about each of these. So let's start off by kind of expanding a little bit on some ball and stick models. So methanol, you can see here with the OH group, phenol as well, OH group. It's this bent sort of 109. It's not. I guess it's not technically 1095. It is. I don't know why my point is up there. Also, it should be down here. Because of the lone pairs on the oxygen, this bond is actually a little bit smaller than 1095, but it's a tetrahedral arrangement. And with sulfur, we don't get into the electronic geometry here. Sulfur has more electrons, but you see that it still forms this same sort of little bend. We call that bent when we see that shape for water, for example. This is this is an H as well. I started drawing atoms and then I guess this turned into an oxygen for me. So this is bent. Ethane thiol, you can kind of see a little bit about the naming here. Ethane thiol is just an ethane with a thiol group on the end, whereas if this was ethanol, or if this was an OH rather than an SH, it would just be ethanol. So that little hint into how the naming goes. So let's jump in. So with the IUPAC system, we're going to replace the E in the naming of our alkane with an OL. So for a CH4, which would normally be methane. We're going to drop the E and add an OL, methanol. There is common names: methyl alcohol, ethyl alcohol, isopropyl alcohol. You've maybe heard of that one, rubbing alcohol. Ethyl alcohol, you've probably heard of as well. Ethanol, main ingredient in alcoholic beverages. That's the alcohol that we drink. So with the common names, we just say the name of the alkyl group followed by the word alcohol. But in terms of the IUPAC naming, we're going to take a compound, something like that. We're going to stick an OH on it, and then we'll name it. This has 1, 2, 3, 4, 5, 6, so it would be hexane. And then instead of putting an E, we add the OL, hexanol. Now, this one, because it isn't, because there's a lot of places where that OH could be. It could be here where it is. It could have been on the end. It could be on the middle one. We have to number it. So this actually would be 2-hexanol. We'll get into that. So 3 or more carbons, you have an OH that can go at different positions. With less than 3 carbons, then that doesn't happen. So you can see here's an example of 1-propanol, where we've got the OH group attached to the end here, the number 1 carbon. If we were to attach it to this side, we wouldn't call it 3-propanol. It would still be 1-propanol. We would just number from the other side. So here we get 2-propanol. As far as butane goes, if we start to, this would be true of propanol as well. If we have 2 OH groups, we call it a diol. So 2 hydroxys equals diol, and actually 3 hydroxys and more, we just add these little prefixes to the compound. So diol, triol, tetrol, pentol. We don't really talk about compounds that way. We have ways of naming them. But this is sort of a descriptor, right? We could say a compound is a diol. We're going to talk about glycerol in the future when we talk about fatty acids in our body. Glycerol is a triol. I can even draw it for you. See if you can name it before we get to that chapter. So here you can see it's 3 carbons long. Each carbon has an OH. This is glycerol. It would be a triol. And according to the naming convention that you can see here, when we have something like a diol, we just say the number of the OH groups. This would be something like 1, 2, 3. So 1, 2, 3. Propane triol. Or, as we like to call it, glycerol. When we name cyclic alcohols, we just put the word cyclo in front. So these are cycloalkanols. That would be the term for them. If there's a substituent, if there are substituents, then the ring is numbered from carbon 1, which is the carbon attached to the OH group. So here, the OH group, no substituents. We don't have to do any numbering, but here we have a substituent, so automatically, because this is a cycloalkanol, we're going to name that carbon as carbon number 1. Compounds with no substituents, again, don't require any numbering. If this methyl had been over here instead of here, then this would be 3-methyl cyclopentanol. We don't have to say 3-methyl 1-cyclopentanol. We don't have to mention that the OH is on the 1. It's implied already that that's how we're numbering. The term phenol is the IUPAC name when the hydroxyl group OH is bonded to the benzene ring. We went over that in the last chapter. When there's a second substituent, the benzene ring gets numbered from carbon number 1, which again, just like in the cycloalkanols, is the carbon with the OH on it. We could use the terms ortho, meta, para if we wanted to describe common names of simple phenols. So for example here, 3-chlorophenol, we could say metachlorophenol, because remember in the 1,3 position we can substitute the word meta. Let's see. Common name cresol is also used for methyl phenols. So anytime we have a phenol, so automatically OH on a benzene, and then there's also a methane group, probably should have circled this one. This has its own name, cresol. So M-cresol would look like that. P-cresol would look like that. And O-cresol or orthocresol would look like that. So give this one a shot, try to name this compound, and I will tell you the answer. Sorry, where's the answer? I guess I didn't tell you the answer. So the answer, if you want to see it worked out, which I guess is what I have to do since I don't have the answer right in front of us here, is we need to number this thing. So 1, 2, 3, 4, 5, 6. I numbered that way because this is a alcohol, so we want the OH group to be on the lowest number. So this is 6 carbons long, so this is 2-hexanol, and it's got a methyl on the 5, so this is 5-methyl 2-hexanol. All right, another learning check. So this time 2 compounds. One is a benzene with an OH on it, and the other one is a variation of what we just did. So give those a shot. And hopefully you came up with those as the base names, and then 4-methyl 2-pentanol for the first compound, and 3-bromophenol or M-bromophenol would also work. Methanol. This is methyl alcohol, the simplest alcohol, found in many solvents and paint removers. It gets oxidized to form formaldehyde. And oxidation, if you guys remember, can be the increased bonding to something like oxygen, but it could also mean losing electrons. It could also mean losing hydrogens. All of these things mean oxidized. In this case, it gets oxidized. It actually does, the carbon here does increase its bonding to O, and it also decreases its bonding to H. So those are 2 definitions. Let's see, increase oxygens, decrease hydrogens, or lose electrons. This is what we call oxidation. And alcohols, well, they oxidize into aldehydes. But anyways, methanol is bad. You don't want to get this in your body. It oxidizes into formaldehyde. And so if you ingest formaldehyde or have methanol becoming formaldehyde in your body, this causes headaches, blindness. It can cause death. Not a good thing. Let's talk about ethyl alcohol. So ethanol, or its common name, ethyl alcohol, it's been known since prehistoric times. It's an intoxicating product formed by fermenting grains or sugars or starches. I've got the equation down here actually for the fermentation. Basically this is a sugar molecule, and this is the ethanol. We get ethanols and carbon dioxides thanks to our little friends the yeast. Ethanol can be used as a solvent for perfumes. It can be used as varnishes. It's used in some medicines. It's also used in tincture of iodine, and actually nowadays other tinctures use alcohols of various types. But ethanol is a safe, well, relatively safe one. It evaporates quickly, and it is less dense than water. Just a couple of random comments about it. I'm actually going to try to brew some beer tomorrow. I ran out of time today. Um, this is antifreeze. This is 1,2, right? 1,2 ethane diol, because it's got two of these. So 1,2 ethane diol. This is aka ethylene glycol, aka antifreeze. It's used in heating and cooling systems. It's used as a solvent for paints and inks and plastics. It's used in the production of synthetic fibers such as Dacron. If it's ingested, it's extremely toxic. In the body, it gets oxidized into oxalic acid, which forms insoluble salts in the kidneys that cause renal damage, convulsions, death. It's not a pretty sight, and it tastes good apparently. So this is why animals that are around it might consume it and then ultimately die from it. This is bisphenol A, BPA. Bisphenol A is used to make polycarbonate. It's a clear plastic that's used to manufacture beverage bottles, including baby bottles. Washing polycarbonate bottles with certain detergents or in certain high temp situations actually disrupts this polymer, causing small bits of BPA to leach from the bottles. So this is, can create a health concern, and so many products often will specify now that they don't contain BPA, but that's the compound here, bisphenol. You can see why it's just got two phenol molecules attached onto this three carbon chain here. In chemistry, we actually see, in nature, we see phenol a lot. We see it in medications a lot too, but here's a couple examples of phenol. We'll see a lot more in the biochem side of this course, but vanillin, eugenol, this is cloves, thymol and thyme, isoeugenol and nutmeg. All of these have a phenol base or a phenol backbone. Again, aromatic compounds is what we call these. Remember? Benzene. Let's talk about thiols. So thiols contain that SH group. They often have strong and sometimes disagreeable odors. They're found in cheese, onions, garlic, and oysters, and they're also used to detect gas leaks. They actually artificially put the smell of natural gas that you would think of in there. Natural gas has no smell. So thanks to thiols, we can detect where there are leaky pipes. Trans-2-butene-1-thiol is the compound in skunk spray. Why is it trans-2-butene-1-thiol? Well, let's check it out. If we were to name this, we already know we're going to call it a thiol, so whatever the SH is on, that's our 1, 2, 3, 4. So this is 4 carbons long. It's got a double bond, and it's got the double bond at the 2 carbon, not between the 1 and the 2 or the 3 and the 4, between the 2 and the 3. So it's 2-butene. 1-thiol, because that's where the OH is, and it's trans because on this double bond, our groups are on opposite sides. When we name thiols, which are also known as mercaptans, so again, also known as mercaptans, when we name these, we add the word thiol to the alkane name of the longest carbon chain, and we number the carbon chain from the side that's closest to the SH group. So we just add the word thiol. So methane thiol, propane thiol. Remember, we could have that group right here, so we could have 2 propane thiol or 1 propane thiol. So you have to specify when you have 3 carbons or more. Here we have 1, 2, 3. So propene, double bond, and it's 1 propene, not 2 propene, which it could be, 1 propene. So we got to pay attention to our numbering here. Okay, yeah, 2 propene, 1 thiol. And that one's found in garlic. So garlic, onions, and cheese here you can see contain all of these thiols. Oh, one other thing about these. Methane thiol, this is a compound that has the odor characteristics of a few things, right? Oysters, cheese, garlic, onions. It's kind of weird that that small molecule is associated with a bunch of smells, and then as they get more kind of complex, they become more kind of specific smells. So methane thiol is probably the culprit whenever you smell something stinky. Okay, let's talk about ethers. An ether consists of an oxygen atom that's attached by single bonds to 2 carbon groups. We can call it R1 and R2. And each of these carbon groups, they can be either alkyl or aromatic groups. So the learning objective here is going to be to write IUPAC and common names for ethers, and to draw to draw their condensed or their line angle structures. So here's some ethers. You can see the oxygen in between some different things here. These are all alkyl. This one's alkyl and this is aromatic. Excuse me. We usually name these with the common name. So the common name gives the alkyl names of the groups, and then we say the word ether. So this has a methyl and a methyl, so we would say dimethyl ether. This has a ethyl and a methyl, so ethyl methyl ether. Or a methyl and a phenyl, methyl phenyl ether, alphabetically of course. If we were naming these according to their IUPAC names, well, that's a little different. And you can see the names here: methoxymethane, methoxyethane, methoxybenzene. So let me explain how that works. So most ethers have common names, but the IUPAC system works by naming something with an alkoxy group. The alkoxy group is made up of the smaller alkyl group and the oxygen atom. So if you look at, this oxygen and look at the two sides and you decide, which one of these is going to be smaller, you can see that the methyl's smaller. So this is our alkoxy group. So the alkoxy is the generic name. So what is this actually? Well, it's a methoxy. So it's whatever that number of carbons would be. Let me draw you another one. So here we look at these two. This has 2 carbons on one side of the oxygen. This has 3 carbons. So less number of carbons, this is our alkoxy group. And since there's 2 carbons, this is ethane or ethoxy. So that's how that works. So once we figure out our alkoxy group, then we name that and we follow that with the name of the long alkane. So here we've got a methoxy on a propane. So it just becomes methoxypropane. My example here is the same. It's an ethoxy on a propane. Let me make it a little bit longer. And now this is ethoxybutane. So there's an alkoxy group, and then you name the rest of the biggest part of the compound as just the alkane chain. So you give this one a shot. This is you giving the IUPAC name for this compound, and then see how you do. So hopefully you didn't just jump through it and look at the end name, but work through it and figure out that you've got an ethoxy and a butane. Now, the problem with this one is that why is this one giving us a name? Hold on a second. I was going to say this is ethoxybutane, but I think they've got the name on the wrong side here. So we've got ethane and a butane. So clearly this is a butane. It's an ethyl group, so it's ethoxy. We don't have to say, oh, we do. Yes, yes. Okay. Why are we saying that this is one ethoxybutane? Because this is the 1, this is the 2, the 3, and the 4. It really doesn't matter about the 3 and the 4, but we could have had a situation where instead of this ethoxy group being attached to the number 1 carbon, it actually could have been attached to the number 2 carbon. So that would have given us, still we would have had a butane here, and we still would have had an ethane group, but this would have been 2-ethoxy butane. Okay, so if you didn't catch that you needed to number it, that's why you need to number it, because there's multiple places on this butane where our ethoxy group could have resided. Okay, good. Ethers. There's, we talked about prophenol. Was it prophenol? I can't remember the name of it now. The compound that I said in the beginning was now I can't even remember what the word is. The anesthetic. There we go. So anesthesia, the loss of sensation and consciousness. General anesthetics are usually ethers. They block the signal to the brain, to the awareness centers at least. They give you some amount of memory loss and a loss of pain feeling and some artificial sleep. This is fluorine here, or isoflurane. This one is inhaled. You breathe this one in. You can see here it's an ether. It's got some carbons. It's got some halogens as well. Now, ether was used in anesthetics for hundreds of years until the 1950s, when new anesthetics were sort of developed. They retained the ether group, but what they did was they replaced a lot of the hydrogen atoms that were on ether with halogens, and this let it be not so volatile, so it didn't just evaporate really, really easy, but it also made it so that it didn't burn so easily. It wasn't so flammable. And so that's why you see lots of fluorines and some chlorines in here. So these are the new kind of improved ether anesthetics. All right, let's talk about physical properties of these compounds. So the learning goal here would be able to describe and classify alcohols by their boiling points, and rank alcohols, phenols, and ethers, again by boiling points and solubility. So this is a hand sanitizer here. This is typically about 60% ethanol by volume. It could be as high as 85%. That means 60% of it is ethanol and the rest is water. You have to mix it with water because alcohols are flammable. Okay, so hand sanitizers are actually a fire hazard in your home. And hand sanitizers that contain ethanol or propanol, they're used to kill bacteria on your hands, but they can light up, and so we have to cut them with water so that they're not as flammable. Luckily, they are soluble in water. Now, alcohols are classified by the number of alkyl groups that are attached to the carbon that has the hydroxyl. So, if your carbon with the hydroxyl has one other carbon on it, we call that a primary alcohol. If your hydroxyl carbon has 2 other carbons on it, it's a secondary alcohol. And if your hydroxyl carbon has 3 other carbons on it, and these could be long chains of carbons, they don't have to be just methyls, we call that a tertiary alcohol. Sorry. So first off, that's just classification. We classify alcohols this way. So give this a shot. Pause the video, see if you can get primary, secondary, tertiary for these 3 alcohols. So secondary for the first, primary for the second, and tertiary for the third. Good. It's important to be able to detect which kind of alcohol you have, because tertiary alcohols, for example, don't react the same way that the primary and secondaries do. So if you can point them out, you'll be able to not get those kind of questions wrong on a lab exam. Because there's a large electronegativity difference between the oxygen and the hydrogen atoms in this OH group, it means that the oxygen has a negative charge, or at least a partial one. And we usually draw that with this little sigma with a negative. Now the hydrogen will then also have a partial positive charge. And so the alcohol down here, this is the hydrogen that has that charge. When these are around water molecules are really into those charge differences. Water molecules that you can see here and here, they're attracted. Those negative and positive charges, they attract each other. This happens in the presence of other alcohols as well. If I brought in another alcohol here, or if I modified this water molecule and made this another methanol. So pretend that this red circle here was actually black. There we go. So this is another, do I have white? No. Let's say that this is another alcohol. You can see that this alcohol here and this alcohol here are attracting each other. The negative and positive attract. The positive and negative attract. So alcohols can stick to each other because of hydrogen bonding. Hydrogen bonding exists because, again, the H and the O in this bond, the electrons are going this direction and hovering around the O and not around the H. So that leaves people charged, or leaves these atoms charged. So in water, alcohols do really well, and they can also hydrogen bond with each other. Take a look how ethers compare with that. Now, ethers only have the O. So the O is partially negative. So it does still attract the hydrogens of water. So ethers will dissolve in water, same as alcohols to an extent. But where alcohols could interact with each other because of hydrogen bonding, ethers can't. Ethers don't have the ability to hydrogen bond with each other because they don't have an OH group. So what that means is we're going to see differences in their boiling points. So alcohols with similar mass have higher boiling points than ethers because the alcohols have that hydrogen bonding that they need to overcome if they're going to boil. So the boiling points of ethers are actually similar to those of alkanes because neither of them can form hydrogen bonds. I think ethers might have slightly higher boiling points just because there might be some kind of polarity in there that might make them attract. Then again, it might actually make them worse at sticking together than a regular alkane would be. Let's see if we can find a good example here. So we've got one propanol, and that has 3 carbons in it. We've got ethyl methyl ether, that has 3 carbons in it. You can see that the boiling point for the ether is 8, where the propanol is 97. So big difference in boiling points just because of that OH group. Same atoms, they have the same number of atoms and the same O and H and all that stuff, same formula, but the way that they're connected. Yeah, I don't have propane on here to compare to, but I think propane was probably in the negatives like dimethyl ether is. All right, and diethyl ether too, you can see is really low. As the carbon chains get longer, the boiling points will go up, and that just is because molecules will tend to interact more with each other and sometimes even get tangled and wrapped around each other. Notice the solubility, though, has the opposite effect. As compounds have 1, 2, 3, even up to 5 carbons, they might still be a little bit soluble, but as they start to have more than 5, they start to be insoluble. And even here, this 5-carbon one is insoluble, and this 5-carbon one is insoluble. So 5 and up, insoluble. So alcohols, remember where our alkanes weren't soluble at all, alcohols up to 4 carbons are more soluble. And if we want to get this 5-carbon compound to dissolve, then we could add another H group, another OH group to it, or another OH group. And every time we do, we add another one of those OH groups, we're going to make it more soluble. So OH is the key. All right. Um, what am I going to show you here? I guess more just about the solubility. So alcohols contain that polar OH group, and that forms the hydrogen bonds with water. So that's what helps it dissolve. Um, and uh, and the solubility of alcohols, of course, will decrease with the increasing number of carbons. One thing that we should mention here is phenol. Phenol is special. Phenol has 6 carbons. So you might think phenol is not soluble. But when we add phenol to water, an interesting thing happens. Uh, First off, because of the way that the ring has that double bond that moves around, that allows this oxygen here to actually lose this hydrogen easily. So we end up with what we call the phenoxide ion. It's got a minus on it. And we end up transferring that hydrogen we lost to the water. So basically we get an acid molecule, a hydronium. Bottom line is, phenol is slightly acidic. Basically, that's what that means. When a molecule can lose an H, it's acidic. So because phenol can do this, even though it has 6 carbons and wouldn't be very soluble, by losing that hydrogen, it gets this charge up here. It gets this negative charge on the O, and that really likes the water, and the water really likes that. And so phenol is soluble, where normally you would think a molecule like that wouldn't be soluble. Here's a couple more examples of some molecules that contain phenol rings um, that are also probably not soluble. Not soluble, too many carbons, but phenol on its own is soluble and becomes even more soluble as you add base to it. If you convert that molecule into an acid, it continues to become even more soluble. Okay, ethers. Ethers can form hydrogen bonds with water, but they can't form hydrogen bonds with each other. They can form fewer hydrogen bonds than alcohols can with water because they only have an O. They're only soluble in water when they have fewer than 4 carbons, and they're not soluble if they have 5 or more. So soluble 1 to 4 carbons. Now phenols, I mentioned that they do have that sort of acid group. These were once used as antiseptics. They're slightly soluble in water. They have an OH group that can form hydrogen bonds if it doesn't just become an acid. It can also react with water to produce, like I mentioned before, the phenoxide ion. So yeah, there's phenol for you. It only ionizes slightly. I should say that it's a weak acid. So if we put this into water, only a little bit does this. So if we want a lot to do this, you got to keep adding base. And base will keep pulling these H's off and turning these guys into these guys, dissolving them. All right, let's talk about antiseptics. I use that term. Substances that are applied to the skin to kill microorganisms that cause infection are antiseptics. These were once just made of dilute solutions of phenol. They were used to disinfect wounds and prevent post-surgical infections such as gangrene. Now, now we use them in like Lysol to disinfect surfaces, and they contain the antiseptics 2-phenol-phenol and 2-benzyl-4-chlorophenol. So these are the antiseptics that we use now instead of just using dilute phenol solutions. So we've added some more benzene rings here, another carbon here, a Cl, and somehow these are better at disinfecting surfaces. Hand sanitizer as well, containing ethanol. A lot of the hand sanitizers contain ethanol, but nowadays you can find, or actually we've converted to ethanol, because ethanol will kill most bacteria and viruses. approximately 60 to 85% is about what you can get in the stores, but that's high enough to do the job. It's very flammable. They produce a blue transparent flame if you ever light them. This is a triclosan. It's an antibiotic compound. It's now banned in personal care products. I'm not sure why. There's a picture of it in the slides, but um, antibiotic compound. So we've been able to use ethanol to do the job that these compounds used to do. Okay. Indicate whether or not you think these would be soluble in water. So pause it, give it a shot, and then check your answer. So A, too many carbons. It's just too nonpolar. B, definitely can do it because of the hydrogen bonding. A does have hydrogen bonding, but too many carbons. All right, let's get to the reactions. This is a flaming dessert, so combustion of an alcohol in here. Probably wine or some kind of maybe just even some ethanol from a beer or something. So combustion of an alcohol follows the same sort of combustion of a hydrocarbon reaction. We're going to have our alcohol here. I'll just draw ethanol. And you would react that with some amount of O2. It'll produce some amount of carbon dioxide and some amount of H2O. Now you'd want to balance it, make sure that you could add a heat, of course. So balancing these, you just want to try to make sure your carbons all match up. So 2 carbons on one side, so we're going to need at least 2 CO2s. We've got 6 carbons, so we're going to need at least 3 waters. That leaves 6 O's. So 6 O's. Well, 7 O's technically. We got to count this guy too. So balancing would go something like that. Now the goal here would be to balance chemical reactions for combustion of alcohols, be able to write dehydration and the oxidation of alcohols and thiols. So let's go over those reactions. So first, the dehydration of alcohols. You remember when we reacted alkenes with water, we called it the hydration reactions. Those produced alcohols. So these are the same thing but backwards. So the loss of an H and OH from 2 carbons that are next to each other will produce an alkene and the water molecule. We call it dehydration. So alcohols will, in the presence of acid and heat, decompose into an alkene. Now, as I mentioned here too, the dehydration of a secondary alcohol can produce the formation of a minor product and a major product. We won't go into too many of the details on that, but the major product is the one that forms by removing the hydrogen from the carbon that has the smaller number of hydrogen atoms. Just like when we were forming it, that's where the hydrogens went. They went to the carbon they went to the carbon with the most number of hydrogen atoms. So this one's kind of the reverse. The major product is where the H comes off of the carbon with the least number of hydrogens, and the OH comes off of the group of the carbon that has more hydrogens. And this is because the hydrogen atoms are easier to remove from the carbon atom next to the carbon atom attached to the OH that has fewer hydrogen atoms. Wait, let me think about what I just said. And we're going to do this example here. This is a secondary alcohol, so we'll get to see what I'm talking about here. So we look here to see which carbon has a smaller number of hydrogen atoms. It's going to be easier to pull a hydrogen off of the carbon that has the smaller number of hydrogen atoms. Okay, this one has 3, this one has 2. We know this OH is coming off already from this carbon. So the other H is going to come from here because there's less carbon or less hydrogens there. So we're still going to have a CH3. We're going to have a CH. We're going to have two bonds because we've lost the OH bond. So there's a HO down here that's going to be a water. We've got a CH because we lost one of those H's. And then a CH2 and a CH3. And then that H went down here. So we formed our water. And we got our alkene. And we formed 2-pentene here, as opposed to 1-pentene. If we had pulled off this hydrogen, we would have formed 1-pentene instead of forming 2-pentene. Now, both of these would form, but the major product is 2-pentene. So I don't know if I gave you a chance to do that one on your own, but hopefully that's the answer that you would have come up with. So practice these. Practice these. So that's the dehydration reaction, removing the water to make the alkene. Let's talk about the oxidation and reduction. So in organic chemistry, oxidation will increase the number of carbon-oxygen bonds by the addition of an oxygen or the loss of a hydrogen. And reduction will decrease the number of bonds between carbon and oxygen. So you can see here with a primary and a secondary alcohol, in this direction is oxidation. So where our primary alcohol had one bond to an O, when we move over here to the aldehyde, you see now it has two bonds to an O. So it had to lose one of its H's. And that's how it does it. It can increase its bonding to O by literally adding O's, or by losing H's. And reduction's opposite. Adding H's, losing O's. So we get an aldehyde when our primary alcohol reacts. And we can do that one more time. We can oxidize it again. This time, since we can't, change any more bonds, we can't remove any hydrogens. There's no hydrogens here to remove. Well, actually, that's not true. There's one hydrogen to remove. So we remove that hydrogen, and that allows us to put another bond, this time to an OH. So the alcohol will go through an aldehyde and then a carboxylic acid when it oxidizes. Now, the secondary alcohols, because they're not on the end, don't look like this when this happens. When we take our oxygen in our secondary alcohol and we remove an H so that we can add a bond to that O, right? There's also another bit where the H gets removed here too. We form a double bond to an O, and we call that a ketone. This is a carbonyl carbon. A C double bond O is carbonyl. And when we find that in the middle of a compound, it's called a ketone. When we have it at the end of a compound, it's called an aldehyde or a carboxylic acid, depending on, what these guys are. In fact, we call it a few more things, an amide or an ester, depending on what's all attached to it. But when it's just got carbons attached to it and it's in the middle of some carbons, we call it a ketone. So let's take a look at these. So here we have the oxidation of a primary alcohol. So it's primary because it's on this carbon, only has one other carbon attached to it. And whenever we oxidize it, we change that to be a double bond. All you got to do is make sure carbon still only has 4 bonds, and that oxygen only has 2 bonds, and you've drawn your aldehyde. We usually show this as the symbol for oxidizing. If this was a real organic chemistry course, we would be looking at oxidizing agents and be talking about what reagents that we would use, but here we can just say oxidize. Aldehydes can continue to oxidize further if we provide more oxidizing agent. And again, we're going to remove the H and add an OH. That's the only thing we can do. We can't remove any H's, and we can't make more bonds to that O. So our aldehydes, so this is part of doing well in this class, you need to be able to recognize when you're looking at an aldehyde, because how else will you know that that turns into a carboxylic acid? And again, carboxylic acid has 3 bonds to an O, where an aldehyde has 2 bonds to an O, where an alcohol has 1 bond to an O. If we take a look at the secondary alcohols, we see that we still have an H that we can remove so that we can make our double bond to the O, but then we're done. There's no more H's to remove, so we can't oxidize further. So this one does not keep reacting. No reaction if we try to oxidize that. And I'm trying to be clear about that with this slide too. This is a tertiary alcohol. Tertiary alcohol won't react at all with oxidation. There's no hydrogen. This is like the ketone situation already, but no H's to remove. So this one also has no reaction and no product will form. Let's take a look at thiols. Thiols undergo oxidation when an H atom is lost from each of the 2 thiols. So here we have the SH group and another SH group. And when these 2 H's are both lost, we form something called a disulfide. We'll look at these more when we get to proteins. Cysteines in the amino acid sequence of your hair, your cysteines form these disulfide bonds, and that's what gives curly hair. So this is caused in our bodies by the amino acid cysteine, but in nature these thiol compounds, these thiol groups, will do this also. This happens in DNA as well with the thymine nucleotide. Oxidation of alcohol in the body. Let's talk about this. So methanol, as we know, methyl alcohol, highly toxic. It's found in windshield wiper fluid, sterno, paint strippers. It's rapidly absorbed and oxidized into formaldehyde and then formic acid. So this could happen in the body. HC3OH. This is formaldehyde. It's an aldehyde, and then formic acid is actually the defense that ants use, or some of them. This ethanol, man, it's a depressant. Kills or disables more people than any other drug. We can actually use a breathalyzer to figure out how much alcohol is in your body. It's metabolized by a social drinker, so someone who's got a metabolism that's like fine-tuned for alcohol, at a rate of about 12 to 15 milligrams per deciliter per hour. And it's metabolized by an alcoholic at a rate of 30 milligrams per deciliter per hour. So the more you drink, the faster you can metabolize it, so the higher your tolerance goes. The acetaldehyde product that's produced from ethanol in the liver. So if you take a look at ethyl alcohol, and then in the liver it gets oxidized into ethanal, or acetaldehyde is the common name. That gets further oxidized to acetic acid, and then it gets converted into carbon dioxide and water in the citric acid cycle. Liver enzymes eventually break down the ethanol, but the aldehyde and the carboxylic acid intermediates, those can cause the damage to the liver cells. So this gets broken down into this and, like I said, acetic acid, which just cause liver cell damage. You can look at this table here and kind of see what the typical behavior is for drinking different amounts of alcohol. All right, learning check. So here's a multiple choice. Select the product for the oxidation of this compound. So pause it, give it a shot. Hopefully you picked B. So if we go back here. Oxidation of the secondary alcohol produces a ketone. All right, and select the product when it looks like 1-propanol undergoes each of these reactions. So first an oxidation, and then a second oxidation. So hoping that you first picked C and then D. So C would be the first product, D would be the second product. You'll do much better at these the more you do, the more practice you do, the more naming you do. So keep up with it, keep doing the homework, and let me know if you guys have any problems. I will see you guys in the next video. All right, take care.